Let's start the delayed plenary session on grid computing. It's my pleasure to welcome you here for this topic. I think it's a new topic which has only been around for a couple of years now. I think the distributed computing is known for a long time, but I think that it's called grid computing is due to my neighbor on the right and his colleague, and I think it really focused the mind of the people on the problems faced by doing distributed computing and remote computing. Anyway, I think I apologize for the late start of this plenary, but Ian had a delay of 3 hours in his aircraft and therefore couldn't make it till 9 o'clock, but he made it after all. And I think it's very kind of him that despite all these problems in traveling and arriving late, he's prepared to give his talk fresh and wide awake, at the moment at least. Anyway, once again, welcome to this session. And there are some announcements I have to make before we can start. initiator of the grid. Thank you, Ian.
Okay. What do I do? There we go. Okay, well, good morning. I'm really sorry about the delay. I would not normally cut things so close, but I had an unavoidable commitment in New York, and then I had the misfortune to fly Continental Airlines. Don't do it. Anyway, what I want to do today is to talk to you about grid computing. I'm sure some of you here are complete experts in the field, and others are less familiar with what's going on. So I want to provide some introductory material and then some observations on some of the more recent directions that we are pursuing. And hopefully that way everyone will be happy. So some of you, I think, perhaps still think of grid computing as something that's sort of vaguely connected with connecting supercomputers together, which is what people used to call metacomputing. That isn't really what we've been about for some time now. A more general statement of the problem or opportunity that we're engaged in pursuing is as described here, enabling dynamically formed collections of individuals or institutions, what we often call virtual organizations, to come together, negotiate resource sharing arrangements, and then use those shared resources for some form of collaborative problem solving. And sometimes the resources concerned may be computers, sometimes data sources, sometimes they're scientific instruments. There's a pretty broad spectrum of applications that fall into this general categorization. The key common elements are a need to be able to negotiate resource sharing arrangements, deal with the security, resource discovery, resource access issues that arise when you're working in a large distributed environment. As I comment here, there's really a couple of different perspectives you can take on this problem or opportunity. One is that it's sort of like the electric power grid, on-demand access to remote computing, data, various forms of enhanced services, and that's certainly an important perspective. The other is that we're concerned with more than just on-demand to one remote thing. We're concerned with coupling multiple things, perhaps multiple computers, storage systems, instruments, to form new capabilities that would not otherwise exist. As Hans said, of course, what we're talking about in grid computing is building on many years of work in distributed computing and networking. In fact, I was just looking again a couple of days ago at a lovely UCLA press release describing the first ARPANET node at UCLA, and Len Kleinrock said, in the future we can imagine computing utilities like electric utilities. So that was 33 years ago, and we're finally now at the point where we can start to think about this for real. And one of the reasons is, I think, suggested by this last quote here, we're getting to the point where the networks, wide area networks, are really high performance, and that allows us to think of computing in a different fashion. So why, where has grid computing come from? One, I guess the initial motivation, like much work in computing, is out of scientific problem solving and computational science. It's a consequence or is motivated by the move from pre-internet to post-internet science, pre-electronic, post-electronic science, with in the latter phases of this development, science being much more concerned with the creation and analysis of large data sets, large-scale scientific simulation, and in general, large-scale multidisciplinary investigations. And in this environment, it's increasingly important to be able to couple together resources from many sources. So I'll just show you a few examples, but let's use one to start with. So this is a very nice picture from the Sloan Digital Sky Survey. So the astronomical sky surveys represent, as probably many of you are aware, so that the first wave of a whole new set of technologies that are revolutionizing astronomy by providing whole sky, multi-spectrum, all digital image collections, which you can then mine for various purposes. Given these large databases, they're currently tens of terabytes, they'll soon be petabytes, you can start asking questions that you would never think to ask before. Like, for example, what is the size distribution of galaxy clusters? So, an individual astronomer could never have conceived of asking that question before, but it's a very fundamental question with lots of profound implications for cosmology. So, you want to be able to take these tens of terabytes of data and then perform a very computationally intensive analysis that looks for galaxy clusters based on their nearness in the sky and their color, which gives you an impression of their distance, their redshift, and then build up a new database of galaxy cluster information. So the way that you can do this in a grid environment, and the way that we've been doing this with people at Fermilab, is you harness a collection of computers at multiple sites, or basically the home institutions in this case of the sites participating in this particular experiment, several hundred processors. You use a grid system to manage the execution of, or discover those resources, manage the execution of the analyses on those resources, to keep track of where data is located, etc. And you end up with with results which show you interesting things, like, for example, the galaxy size distribution is basically a power law distribution. Interestingly, the same sort of distribution that you get for link frequencies in the web. So there are analogies between the World Wide Web and the basic structure of the universe, which is perhaps interesting. Anyway, so that's the sort of thing that one example of the sorts of things that people want to be able to do. Now, in order to do that, that's a very small-scale example. In order to be able to pursue these things in general, we have all sorts of interesting problems. How do we form and manage these virtual organizations? How do we negotiate access to resources? How do we configure our applications and systems? These are all problems that certainly touch upon things that networking people normally think about, issues of certainly network performance, certificate authorities, directory services, and so forth, but that also require a set of new capabilities relating to higher level middleware. The technology that most of these projects are building on, there's certainly a lot of technology beyond this, but the core technology that most of the eScience projects are building on at the moment is this Globus toolkit that we've been developing for some time, and that now has many contributions from, in fact, from Europe and other US and Asian groups. Basically, this takes as its starting point the technologies that have been put in place in today's networks, and then builds on top of that machinery for authentication, with support for delegation, very important, resource discovery mechanisms, support for reliable invocation, etc., etc. A whole set of basic mechanisms that you need in order to create the sorts of applications that I just described. A fundamental aspect of the design of the system is highly information-centric structure in which resources, services, in some cases applications, are self-describing, so that we can dynamically discover what resources are available to us, what they look like, how we should configure them, where we might be able to run our application, and so forth. Globus, I think, has gained a lot from being open source, so it's great to hear that Unicore is going in the same direction. In fact, we're starting to work very closely with the Unicore group as part of the GRIT project. So one thing that has happened over the, we've been doing this grid stuff for a little bit more than 2 years, but over the last 2 years, we've started to see this move out of the lab, if you like, so we're not viewed as eccentric people playing with networks, and into the hands of real scientists. And one thing that is produced is a wonderful set of logos, as you can see. But seriously, each of these logos and many more represents a significant effort, often by large communities of real scientists who are trying to apply grid computing technologies to further their science. They're not particularly interested in in grids for their own sake, but they do want to do their science on a larger scale than was possible before. Just to talk about scale, I mean, this is a slide that some of you probably have seen. This is one of the, I talked about virtual organizations. This is one of the larger virtual organizations, the various groups participating in the Large Hadron Collider, certainly not the only one, but perhaps one of the bigger ones. And this slide, captures the sort of system that they want to put in place, something rather like what I talked about for the Sloan Digital Sky Survey, but on a even bigger scale, spanning multiple continents and countries. And so, I think those of you who are networking system administrators or operators can see some of the, for example, authentication, authorization, resource discovery challenges that we face when we're building systems like this. And in fact, there's been a lot of work recently just on the mundane issues of negotiating certificate authority policies between the US and Europe. In fact, we are currently cross-certifying and accepting certificates between European and US data grid groups. Another set of issues which have certainly not been resolved relating to how we do grid operations, how we address grid operations issues, how we diagnose problems that arise when people are running large data-intensive computations across systems like this. I wanted to just make clear that grids, contrary to what you might hear from on some occasions, are not just about physics or data. There are people, for example, at NASA who've been working for several years on applying these technologies to enable large-scale multidisciplinary simulation in the aerospace industry. So here the interest is in coupling simulation codes that exist in different places for either proprietary or perhaps just convenience reasons. There is very interesting work going on in many places. Here I show some work at the University of California in San Diego using grid technologies to connect instruments, in this case electron and light microscopes, with computers and with remote users. So there's a broad spectrum of applications. What I wanted to say a few words about is, because I think this is ultimately going to be very significant, is what does this all mean, not for us poor scientists, but for industry. And we've just, I think, started to find out over the last year or so that, contrary to what some people initially thought, grid computing is not just something that scientists care about. It's sort of like the web, at least that's the current belief. It's something that has broad applicability because in industry, in many aspects of industry, you face the same need to be able to allow dynamically formed groups of departments within an enterprise or enterprises or producers of technology and consumers of technology. You want to be able to form those groups to come together and engage in various forms of resource sharing arrangements. And some of the motivations for that, so my commercial friends tell me, is first of all the fact that the enterprise infrastructure of today is becoming increasingly fragmented and distributed for various reasons relating, for example, to the increased focus on the use of commodity servers and intelligent network devices, so-called, and various forms of transaction processing, web workloads. The rise of this concept of the utility computing, IBM, HP, a whole bunch of other companies are promoting that, claiming that they can achieve economies of scale. And of course, as I just said earlier, these various business-to-business computing scenarios. So that's got a whole lot of people in the US in particular, and I think also now in Europe and Japan, interested in how you might be able to apply grid computing in an industrial context. So this is a picture provided by one of my colleagues at IBM, illustrating the problems that they face. So they want to be able to take a collection of resources like this. This is a single enterprise's computing environment, and then somehow tie these resources together and deliver some qualities of service, whether security, reliability, performance. And their perspective is that there's a lot of similarities between what you have to do here and what a astronomer has to do when they're trying to tie together resources from multiple institutions and support a data analysis workload. So I wanted to show just first, you've probably seen various press releases and so forth about grids in industry. There are actually companies out there doing simple things already in an industrial setting. So here I show two examples. One of them you've probably heard of, Entropia is one of a number of companies. United Devices is another that's doing sort of grids in the small, allowing people to exploit idle machines within an enterprise, for example, for pharmaceutical design. The other one you may not have heard of, but it's an interesting example. Butterfly.net recently announced that a new product in which they claim to be providing support for multiplayer games. So, it's a bit tiring sometimes to hear about science applications. Well, here's a very much a mass market application for grid computing. They have millions of game players, fairly dynamic demand, and they want to be able to dynamically provision the computing and storage and network resources that are required to support those interactions. So we'll see how they do, but they, like essentially everything else I'm talking about, are building on Globus technology. So this is all I'm going to say about business, but I thought it's interesting to provide this perspective to you. So it seems like there's a new set of forces working on grid computing, which are going to, I believe, change everything that we're doing pretty fundamentally in the next year or two. And they relate to industrial people in industry trying to leverage grid computing really for three things. First of all, to enable on-demand access to computing, storage, and services. This is sort of the outsourcing computing utility model. Secondly, using it to enable new classes of applications based on on-demand access to computing and high-speed resource integration. And finally, what I referred to earlier, using grid computing to do a better job of creating manageable distributed infrastructures within an enterprise. And we'll see exactly what that leads to, but I think it's a very promising set of directions. So this is why of course, people in the press aren't interested in science, but they do listen to IBM, and so it leads to press stories like this where we find out that grid computing is the next internet. So that's obviously vast hyperbole, but it's still shows that people are to some extent paying attention. So now what I want to do is go on and talk about some specific technology issues. So if we want to realize the promise of grid computing for both eScience and eBusiness, there's a set of challenges we need to overcome. So this is really a business-oriented slide, but the issues are really the same. So we need to understand how to build infrastructure elements, power plants, much better than we do today, so that we can deliver computing and storage and other services on demand in a grid-enabled environment. We need to work out how to actually build applications and tools that can work in a distributed, dynamically provisioned environment. We need to new application concepts, and there are issues of business and service models which don't really affect us so much in science, but certainly do in other areas. What I want to focus on is just the second of these, which is how are we going to go about building, what are the mechanisms we need to put in place to support the creation of infrastructures and applications and services that can exist effectively in this environment. So this is going to lead me into saying a few words about some new directions in grid computing, which we're calling the Open Grid Services architecture. So, I referred earlier to the rise of the Globus toolkit as a de facto standard for grid computing, and in eScience it's been very successful. And basically, I think it's been successful because it incorporates technical solutions to a set of basic problems that people encounter when they try and build distributed applications. So it provides some mechanisms for single sign-on, for reliable, secure invocation, for resource discovery. The actual design of the toolkit is, from our perspective, somewhat outdated. It's evolved by accretion over a number of years. So about a year ago, we started thinking very hard about how we might redesign it to, first of all, refactor. That's a term from software engineering. Pull out components that were useful so they could be used in isolation rather than having to be used only within the protocol where they were incorporated. And secondly, looking at how we might adopt some more modern software interfaces and technologies that were coming out of industry. We also then got started about 6 months ago talking to people in IBM who had similar interests, and this led to a very effective collaboration that produced an early specification for this Open Grid Services architecture. And what this involves, as I say here, is a refactoring of the Globus protocol suite, and we'll look at what that leads to in a second. Adoption of a service orientation as a means of virtualizing resources so that you can, for example, you define a resource by its interface. So this is not, of course, not rocket science, but it's a new technology, at least in the grid domain, so that, for example, a database or a program that looks like a database that simply responds to requests for information by computing it have exactly the same interface and look the same. Or a single workstation or a global, in fact, a national or a global pool of computing resources can support the same interface. It's very important in terms of being able to build reusable abstractions. And then, very importantly also, we decided to embrace a set of technologies which I'm sure most of you are well familiar with, so-called web services technologies, which are proving to be quite popular in industry. From our perspective, they provide a standard interface definition language which we find desirable. And there's also hopes that we'll be able to leverage significant commercial efforts in this area. For example, there's a lot of work going on with various forms of workflow systems on top of web service mechanisms, and a lot of work going on in terms of web services security, for example, two things that are pretty vital for us and we hope to be able to leverage. So what came out of this is something called the Grid Services Specification, which is basically an evolution of the Globus toolkit and a recasting in terms of a set of standard interfaces and behaviors for what we call a grid service, an entity that exists in a grid and supports information services, security services, and the other things we need for distributed execution. So let me say a few words about the Open Grid Services architecture. Now I'll take a perspective that tries to contrast it with basic web services. So as probably most of you know, the main point of the web services framework is to allow people to describe, in terms of an interface, discover via some form of directory, and then invoke operations on network services. And a traditional web service is something that sits on your network and maybe provides access to a corporate database or allows you to, for example, ask, in America, the example people usually use is it gives you the current stock prices. In England or Ireland, it seems to be, tell me the current weather. I guess it depends on your relative interests. But the main point is that web services is mainly about providing access to information about persistent services that sit on the network and you don't expect them to go away anytime soon. In grid computing, of course, we have persistent services. There are big databases and there are computers and other resources that we want to provide access to. But in many cases, we're also interested in something somewhat different, and that is activities that involve the dynamic creation of state, the creation of computations, and the management of relationships and the lifetime of those dynamically created entities. So what we want to be able to do, in fact, is create transient services in a network. So, for example, if I'm engaged in a workflow, some sort of distributed workflow of application like my astronomical data analysis example, I'm going to, first of all, go out, discover computing resources, application codes, and so forth, that's, there I'm dealing with persistent services. But then I'm going to want to be able to create new dynamic processes concerned with performing computation, perhaps with staging data, perhaps with storing the output of my computation. If I'm dealing with a video conferencing session, maybe the transient services and the state associated with them are concerned with membership services, network reservations, maybe various forms of transducers that map from one format to another. And the big sort of realization that we had when we started looking at web services and grids was that a lot of what we've been doing in grids for the last 5 or 6 years is mechanisms for dealing with transients and state management. And so what we end up doing in OGSA, in fact, is taking those mechanisms and encoding them in terms of interfaces and behaviors for naming, managing lifetime, creating, discovering transient service instances. So, anyway, so the result is the Open Grid Services architecture. It's a set of web services description language, that's the web services IDL, interfaces and behaviors. And we define, as we'll see, some required and optional behaviors. Some WSDL extensibility elements, which we're currently, in fact, next, I think in 2 weeks' time, we'll be discussing with the W3C in Paris. And then, as in the past, the goal was to deliver this stuff via high-quality open-source software. The Globus Toolkit 3.0 is going to be based on these mechanisms. What's new is we're also going to see commercial implementations. So IBM is committed to supporting these interfaces in their WebSphere and DB2 and other products, and we're expecting to see other companies following suit. In fact, there's 4 or 5 that have already made commitments. So let me try and explain briefly what these mechanisms look like. So we're the basic issue that we're concerned with is how do we, given that we've decided that everything in a network, whether it's a resource, like a computer or a program that's, an application program or a database or something like that, is going to be accessible in the same manner via a standard interface definition. So the question is, what should that resource look like, and what are the basic behaviors that any such service, I should say, not resource, should support? So what we end up doing is we define a set of abstractions. A service has an interface, so that's standard web services, and those are those little squares up here. Oops, I guess I can use this. Does this work? Maybe not. Okay. Okay, those are these little rectangles at the top. We introduce a new concept, and that is this notion of externally visible service data elements, so that associated with a service. So if your computer encapsulated by one of these interfaces, you'll have a set of service data elements that are externally accessible. If you're an application program, you can have a set of service data elements. And these service data elements, just like I talked about the Globus Toolkit in its current instantiation having this information-oriented model. So this is the same concepts recast in the web services form. Each of these service data elements, as we'll see in a minute, is a set of typed, named XML with some nice lifetime information, so you can manage lifetime. So we have a standard representation for information about entities. So in that's the basic elements. Now we start to define interfaces. So we first of all define one required interface. So any grid service has an interface that allows you to get at its service data elements, and secondly, to manage its lifetime. And you can manage its lifetime either by explicitly destroying it, that's puts paid to its lifetime pretty quickly, or you can use soft state lifetime mechanisms to dynamically extend an initially negotiated lifetime. And this use of soft state lifetime mechanisms is pretty fundamental to every aspect of the OGSA model. So for networking people, soft state techniques are very familiar. Of course, they're the basis of RSVP and all sorts of other things. But it's a sort of, I think, a new concept in the context of programming languages. So Genies, with its leases, has some similar ideas. So that's one required interface. We then define a set of additional interfaces that address things like notification, authorization, service creation, service registration, concurrency, manageability, and so forth. And of course, you can define arbitrary application-specific interfaces if you wish. Reliable invocation and authentication are viewed as binding properties. So one interesting aspect of WSDL is you can, for a single interface, you can support multiple bindings, and we take advantage of that quite a bit. Now, so the last thing I'll say about this slide is, I'm, as with any good encapsulation system, having defined these interfaces, I can provide many different implementations, and in particular, I can provide implementations in different hosting environments. So we're currently pursuing J2EE and C implementations, and there will be a .NET C# implementation as well. So you'll be able to build applications that link together, scientific applications and running in a C hosting environment, others running in a Java applications running in a J2EE environment, and also systems running on Windows platforms. So I said something about service data. Let me just say a few more words about it. I mentioned soft state lifetime as being fundamental to everything we do in OGSA. So one concept we take from the current Globus toolkit, the current monitoring and discovery service, MDS, is this notion that information about entities always has lifetime information associated with it, so that as that information propagates from its source through the network, I can keep track of how timely the information is and whether it's time for me to refresh the information by going back to the source. And one neat thing which I won't have time to say more about is the service data component is very nicely integrated with the various notification interfaces, so that I can, given a set of service data, I can request to be notified when it changes, and I can use that that notification mechanism to be notified when new services get created, because a registry service has service data that defines the services it knows about. I can use it to be notified when new operations are supported, because a factory service has a service data that just defines the set of operations that it supports. So there's a very nice integration of these different components of the model. Okay, so I wanted to, use, oh, can I go back? Yes. I wanted to just use an example now to bring this all together in the time remaining. So first of all, I'll show you this slide, and then we'll go through a more realistic example. So what does this look like for someone building a real application? Well, here's a simple example of a service that we might construct. Let's say we want to define a OGSA interface to some form of database, whether it's a Oracle or a DB2 or some other. Maybe it's just a program that supports a database interface. So in a web services environment, I would define as a WSDL interface specification a DB access service that might support a query operation and an update operation, and maybe some other concurrency control operations. In a grid service environment, I'll add in this grid service interface so I can do lifetime management. And I'll also have a few service data elements. I'll have one associated with the grid service, which gives basic information like its name, lifetime, other sorts of things. And then for the database access interface, I'll have perhaps things like the type of the database, the query language it supports, its current load, and so forth. We could also add in a notification interface so that I could, for example, request to be notified if the load on the database goes above a certain level, if I'm concerned with system management, or I might request to be notified if new data becomes available, if I'm a user of the database. Okay, so now let's look go through an example. So I'm assuming I'm a user in a grid-enabled world, so that I don't have to maintain all my databases and computers myself. Rather, there are various entities out there that run compute service providers and storage service providers and databases, and I want to do something interesting. I want to mine a set of data from multiple databases, to create a new database containing information just of interest to me. So I will first of all contact a registry service to find out where relevant resources are available, be told where those resources are, initiate requests to create new services on those resources, specifying initial lifetimes. The minor service will start doing its job. I will meanwhile indicate continued interest by these soft state lifetime keep alive messages. Results get returned to the database. The miner goes away, and I'm left with a newly created grid entity, a new database which contains the information I'm interested in. And now I can perhaps either use that for my computations, discard it, or make it available to others by appropriate manipulation of authorization information. So that's all I'm going to say about OGSA. I've just got 2 slides to go here. Wanted to say a few words about our plans. So we're in the midst of implementing a next generation Globus toolkit based on these mechanisms. Where we are at the moment is we've got this work is going on in very close consultation with, I should say, the OGSI and other working groups in the Global Grid Forum. So there's a OGSI grid service specification document which is undergoing significant debate and revision at the moment, and we in the Globus project have a reference implementation that we've constructed, which we just released last week, in fact, for others to look at, and so far we've had several hundred downloads. This is, as the specification firms up, this will become the GT3 core, providing the basic services I've been describing to you. We will then implement over the next few months first a prototype, and probably sometime next year a production version of the current Globus abstractions and interfaces layered on top of these core mechanisms. That's the GT3 base services. And then in consultation with and cooperation with many others, we're going to start building a rich set of higher level services. And we're already seeing a lot of buy-in and cooperation in this area. So for example, the UK eScience program has made a significant commitment to contributing database services based on OGSA mechanisms. In fact, they are well along in terms of defining and starting to implement those things. And we hope to have a lot of other contributions also. So if I could summarize, so you already know about the grid, so I won't say more about that. We're very excited about this work on the Open Grid Services architecture. It seems to advance the technology, to some extent, but in particular by adopting a standard interface definition language, it makes it, I think, much easier for the community to come together and start to build up a rich set of interoperating grid services. And of course, the fact that we have industry engaged in helping to define this and also helping to implement it, I think, is a very strong positive in terms of our ability to continue to move forward and also have influence on others. That's my final slide. If you want more information, the important thing on this slide is to remind you, if you don't know about it already, that the Global Grid Forum meeting is taking place in Edinburgh in July, immediately followed by the High Performance Distributed Computing Conference, and I hope that we'll see some of you at that meeting. Okay, thank you.
Well, thank you, Ian, for your presentation and about the... I think we leave the questions to the end of the plenary and now have the next talk. It will be given by Tony Hay, who will talk about the UK eScience program at the grid. Tony is the manager for the eScience core program in the UK, and I'm sure he will now give some implementations and projects which are supported in the UK.
Forward is what?
Tony?
Okay. Fine. Thank you very much, Geerd. Thank you, Ian. What I'd like to tell you about is some of the projects that we've put together in the UK, building collaboratively on work done in the US and elsewhere in Europe, the data grid and so on that we've heard about. So, first of all, my boss, if you like, the head of the equivalent of the NSF, is the Office of Science and Technology. John Taylor, who used to run Hewlett-Packard's research labs, defined eScience as global collaboration in key areas of science. And the next generation of infrastructure to enable it is what I take to be the grid. So the attitude that I have to produce as director of the eScience core program is to support the applications. So they're not just traditional supercomputing applications. Many of them are data oriented. So we have, of necessity, a slightly different focus in the UK than the traditional one. And also there was a desire to engage industry to learn the lessons in the challenging scientific applications and build bridges to industry so that they would be robust industrial strength applications for scientists to use, but also that would feed into industrial applications along the way that Ian indicated. So what I will be talking about is what's called the eScience Initiative, which is I don't have a euro symbol on my laptop, so I've called dollars, which is roughly the same. So it's a $180 million program, more or less, for the next 3 years. eScience Initiative. But I thought it would be interesting to point out that there are other funding routes in the UK. This is mainly for middleware and people. This is actually mainly for hardware, high-performance computers and so on. And this is for a component that is often missing. It's not really the research component, it's really the development component. So I'll say a little bit more about that in this talk. So the UK eScience Initiative, which is primarily about, is this €180 million programme over 3 years, of which the majority is for launching applications right now, trying it and learning how to use grid technologies to do better science, and informing, therefore, the development of the grid technologies. 50 million of that, the remaining 50 million, is for the core programme, which is to engage with industry and also to learn lessons for generic middleware coming from the applications and to pick up with industry bits of software that we can make into more robust industrial strength versions. And to do this, we require matching funds from industry of around 30 million of that 50 million. So that's what I'll tell you about mainly, but the research funding, equipment funding, we have, as I said, $100 million or so, which funds not only a fairly competitive system, which should be installed in October this year, of 3 teraflops going to 6 to 12, and also there is also another stream of funding which funds large-scale clusters, 300-node clusters, or modestly parallel shared memory systems in universities, departments, or even groups. So that's the equipment funding that we have. We also have, in contrast to, for example, the USA, we have funding for a national research and education network called National Academic Network, SuperJanet. We also have metropolitan area networks which connect the universities, and this is the sort of structure. There's a backbone here, which at the moment is 2.5 gigabits, which will go up to 10 this summer. And linked to this are these metropolitan area networks with universities on the edges. So that makes interesting issues like quality of service end-to-end and so on. We're also looking at the possibility of funding a Lambda connection to Chicago and to Amsterdam, if you like, a UK-like technology, looking at different ways of looking at quality of service. And so there's a funding stream that could enable that. There is also a more development, if you have an R&D project, this is more the development side, looking at authentication, authorization, and accounting, and we're just putting a call out now, looking at to do something in that area, linking, as we heard in the Internet 2 presentations, from the grid communities to the sort of campus organizations and multi-campus organizations. So this is really what this is, a link between grids and more general academic campus computing. And we're also doing a requirements analysis with the research councils. What do they need to support their research in the way of networks or infrastructure, middleware, and so on? And there is the possibility of funding a digital curation center looking at how you will actually store and curate in the long term all the petabytes of data, scientific data, primary and secondary data that you'll generate in all these eScience experiments. And so, if you like, it's like a digital library, but it's a digital library with visualization, transformation services, as well as the traditional digital library services. So that's SuperJanet I've talked about. The eScience projects, I'll quickly tell you a little bit about some of the eScience application projects. Then I won't say very much about the particle physics and astronomy. You've heard a lot about data grid today, and you've also heard Ian talk about the astronomy type applications. So I will actually focus on 5 of these engineering applications, which are slightly different and more data-centric. And there is also a high-performance computing one, which I won't talk about. And there are other ones so these projects have been going about a year, 9 months to a year. These projects are just getting started. So there will be some content to talk about in a year's time from these biology, medical and environmental ones. But the engineering, particle physics and astronomy are more mature and are beginning to get progress. So this is the particle physics one. These are the universities in the UK. They're, of course, linked to the community of the data grid community, and this is the foil from Les Robertson at CERN. You have at the top there the LHC producing petabytes of data, and what you need to do is you need to do a reconstruction, you need to do analysis, you need to do event simulation. Large amounts of computing on large amounts of data, and if you analyze how much computing you have on a fixed budget, this is what you can afford at CERN. This is the sort of computing requirements you need. So you have to do something to distribute data and computing, and as Ian showed, the community is widely scattered, and that's really a global collaboration. You have to deal with moving large amounts of data, computation, and so on around. And as we heard in the data grid session, they're making good progress in putting up prototype grids to do that. This is the UK version of the NVO, or the AVO, the European Virtual Observatory, and this is the same rationale that Ian talked about before, looking at different spectra, trying to find different analysis by looking at the sky and all the spectra from the gamma ray right through the visible up to the radio and so on. So there are many challenges there. But let me talk now to some ones which may be less familiar to you. This is a chemistry project, combinatorial chemistry, unlike the chemistry I used to do when I was at school, where you had pure samples and you mix them together to get a pure sample. Here you make many compounds all at once, and you generate, again, a deluge of data, which you need then to compare with, to analyze and automate the collection of metadata with the data, because otherwise you will not be able to construct search engines to find the things you want. So you really want to automate putting metadata with the data as you store it. You want to compare with simulation models and with also models in the literature. And so there's a couple of universities involved, the Cambridge Crystallographic Data Centre, and a couple of companies, Pfizer and IBM, are involved in this project. And their goal is something like this. They actually have remote control of an X-ray crystallographic device. You can send your sample, and then you can control the device and take what measurements you want remotely. You also have the analysis, simulation, and you have a wet lab over on the far side where you actually are actually getting the data. And you also might have video data up here which you want to keep. So there's a lot of data, and I put Globus here as a sort of catch-all. That's not necessarily the properties that Globus has at the moment, but it's what the properties you need to have for the grid to support this experiment. It has to engage all those aspects. The MyGrid project is a biology project and is bioinformatics, and again it's to deal with getting data from a very diverse set of resources, not only the genomes, which are just sequences of letters stored in a few sites around the world, in the US, in Cambridge in England, and out in Japan, but also the molecular structures of the proteins that the genes produce, and you want to actually correlate that with possible target chemicals, and possible gene profiles of individuals. And so that's what they really wish to do. They wish to support the experimental process of data accumulation with a sort of workflow, so it's process enactment, and they want to use all the information that's out there. And again, it involves the European Bioinformatics Institute and some universities and some companies, GlaxoSmithKline, AstraZeneca and Merck, who are not, of course, giving all their IP into this project, but they wish to learn from this project and then take what they want back into their in-house systems. So it's an interesting challenge in managing intellectual property. So this is the sort of data, large amounts of data generated of very varied types. So it's a much more varied and difficult data challenge than something like the particle physics challenge, where the data is all of the same character. There's a lot of it, but it's much more homogeneous than this type of data. So you really wish to do data federation, data mining, not only relational databases, but also trying to do semantic joins as well across different types of data. And also, again, you also wish to link up to the published literature over there, which is conventional scientific literature archives. So it's a very exciting and interesting problem. And this is what they hope to generate with this project. As Ian said, this is one of the drivers for actually focusing on data access from databases and other data archives. Process enactment, that's the workflow aspect, personalizing metadata, and eventually automating this with agent services. And the belief is that putting this with ontologies will lead to a much more, Tim Berners-Lee talks about a semantic web. This is, if you like, a semantic grid where you actually have an intelligent grid. You can do different types of... this doesn't work, is that right, this laser? Oh, it does work, yes. You put grid services with ontologies to get a semantic grid. And so that's the ambitious goal of this experiment, and they've made some progress, which they'll be reporting on in September. Another project is again based on data mining and knowledge. Again, it's a sort of like a data warehouse, but this time using not only biodata, but also environmental data from sensors that you can plaster, very cheap sensors which can radio data in and so on. So you'll have a huge data deluge, potentially, from environmental sensors. And again, you have to worry about diversity of the resource, normalization, cleaning, the normal sort of things you do in commercial data warehousing. Information issues, how you actually put the metadata on that XML and schema and so on, and then how you extract knowledge. And so this is, again, emphasizing the knowledge, and they have this sort of picture where they have a discovery process markup language, and there is services that they offer the user. So that's focused on high throughput devices. Bioinformatics is one of them, but also environmental sensing. This is a different type. This is health maintenance. This is industrial health maintenance, and this involves a number of universities and Rolls-Royce and their data systems. As Ian flew from Newark to Ireland, the Rolls-Royce engines on his plane, or maybe they were not Rolls-Royce, but Rolls-Royce have about 100,000 aero engines out in the field. Most of them are flying most of the time. And the sensors on those engines for vibration, temperature, pressure generate about 1 gigabyte of data per flight from across the Atlantic. Now, you can't store all of that, but what they would like to do is they'd like to monitor that, at least a selection of that, against their data center, where they have well-known documented problems, and they do a sort of intelligent, it's based on a neural network search program, to see if there's an incipient problem arising from vibration or whatever, and they can integrate their maintenance center and their ground station, so when the plane lands in Shannon or wherever it is, there's a part waiting and you can replace the part, so you can increase the time between scheduled maintenance where you have to take the engine off the plane and so on, and that's an expensive business. This is in the context of industrial healthcare, but you see it has many applications in conventional healthcare as well as in other industrial aspects. The last industrial project is again emphasizing on the knowledge and the data. This is intelligent design. It involves Rolls-Royce and a CFD company, Fluent, Microsoft, Intel, and a few small companies here. And what they're trying to do is develop an intelligent design where you actually learn from your knowledge repository about what you did last time with your designs and the lessons you learned. You try and capture that. You use it with your actual computation of your new designs with CFD, finite element, and CAD systems, and you put all that together to make an intelligent design system. And the intention of that, commercial benefits for that, why industry interested? Because they want to reduce the time to market and increase their design cycle, speed up their design cycle. So those are the projects that I'm required in my role as the core program director to support. So I need a grid middleware that will allow me to do that. And Globus does some of that, and it addresses some issues like the security issues with digital certificates, as you heard from Ian, in a good and pragmatic way. But there are other aspects that at the moment are lacking, and those are the ones that we're working with the Globus team and others to develop. So these are the sort of elements that we've put together. A network of centres, because we believe you have to have these are the centres that we've established, where we have each of these centres are donating resources to a national grid, and what we are making them do is put up that national grid with the same software, so you can actually have a persistent grid and learn about the difficulties of running a persistent grid. Many of them are sociological difficulties, because you have the scientists who want to do science, you have the computer scientists who want to do computer science, and you have the computing services who have to run a service for the universities. And you have to convince the people who run the firewalls, the computing service managers, that you will allow people who aren't registered on your site to use your resources, to get through your firewalls. And that's a very great challenge. The NASA grid that Ian talked about, the information power grid, was basically 4 NASA laboratories. It was within one organisation. Here we have 9 different universities, each with different policies, each with different securities systems and so on. And actually making that work is a very educational experience. And we're partway there. But we've got further to do before it's actually a really useful resource for people to use. So building a UK eScience grid we see as a very important way of getting enough people up to speed with the difficulties of really doing distributed computing, distributed data federation in real, for real. We also then are working with industry. We have some grand challenges. CS stands for computer science, eHealth grand challenges, and a few other aspects. So I'll quickly go through those. So that's the network of centres. Each of them has an access grid node, which is an interesting experimental way of doing collaboration. Whether it's the best way of doing multi-site video conferencing, we don't know yet, but certainly the user experience we have is that people like it and find it useful. So we are working again with the Argonne Rick Stevens team to see whether we can develop it further with them. What about timescales for industrial exploitation? We are to talk to industry, and we have a 3-year program. That's a very short time. IBM see early adopters of grid technology coming from pharmaceutical, engineering and petrochemical sectors, where there are clearly the potential that they're willing to look at some bleeding edge technology. What we see is very similar. In our projects we see AstraZeneca, GSK, Merck, Pfizer, pharmaceuticals. We see Rolls-Royce, British Aerospace from engineering, and Schlumberger from the oil. So we see a rather similar picture to what IBM talk about. And Wazowski-Berger talks about this becoming mainstream 2003-4, which is not a long way away. It remains to be seen whether that's over-optimistic. Other companies, as you've heard, are talking about it, Microsoft and Sun. These are quotes from them. Grid computing is one of the 3 next big things for Sun and our customers. The other 2 big things are, one is actually real time and the other one is wireless, according to Mr. Zander. And this is Microsoft, an important statement here. The Open Grid Services architecture with XML web services, they believe, will make internet scale grid computing possible. So I think it's very interesting that we have IBM, Microsoft, Hewlett-Packard. I think there is really considerable momentum behind this, and it could really become robust enough for businesses to use. So these are the collaborative industrial projects that now we have, like in European Union project, you have to have government money, but you have to have matching industry money, so they're only going to put it up if they see some benefit. What we have, the application projects I showed you have 15 million of industrial input. We've also allocated to each of our centres a budget for industrial projects, and so far about 8 million of the 24 million euros has been taken up. And these are some of the projects. A portal project with Sun, open source cluster software with Intel and CompuSys, a telemedicine project, a molecular informatics repository with Unilever. This is middleware software tools and technologies with Hewlett-Packard. And I'll tell you a little bit more about the grid data project, because that's one of the focuses that we see is important for our projects. And as you know, academic research projects are not noted for delivering software that other people can use, that is documented and really works. So we really need to ensure that we do better than a normal academic R&D project and deliver software that other projects can use. So the space that we're looking at, I think the grid started out here with rather low data complexity but rather large computation. The web traditionally sits over here. Tim Berners-Lee's talking about a semantic web up here, and what we're looking at in the applications that we're talking about sort of sits in this space up here. So that's the area where our projects need help, and the Open Grid Services Architecture Data Access and Integration Project is to develop high-quality data-centric middleware for use by these projects, but also by industry, and we're therefore involving IBM US, IBM Hersley, who are a middleware lab in the UK, and Oracle UK are helping manage this project to produce robust industrial strength software, which is better than the normal sort of research level software that I would produce, that is sometimes documented and sometimes works. We're also looking at some areas clearly of interest to governments, and this is one of the areas of e-health, and we have a number of technologies projects already existing. The Equator project looking at human-computer interface with the physical world with the digital world, and advanced knowledge technologies and dependability of computer systems. So those are three existing long-term research projects in the UK, and we have also another project looking at medical images and signals to clinical information. And the idea there is you take something like a digital mammogram and you actually do a modelling of breast tissue with analysis of the mammogram, and you want to get the technical data into a form that could be used by a surgeon in the operating theatre. And again, what we're looking at here is producing a MIAS grid where you store the digital mammogram information with metadata so it can be used as a national repository for doing epidemiology and things like that. So the projects that we funded, joint projects using these computer science technologies with this application. One is, if you like, a decision support system for breast cancer, trying to integrate clinical, radiological and cytological data, so sort of data fusion supported by AI knowledge tools and so on. And the other one is a wireless technology where you imagine that you walk around Limerick with sensors all over your body recording your heart rate, your temperature, your blood pressure, and maybe the amount of drug being injected during the day. And if you see anomalous signs, you can bring people in. But if you have 200,000 people walking around all sending signals in, there are clearly interesting issues to be sorted there. So these are two sort of rather research projects, but we think potentially with large payoff. And that's the sort of project that we need grid middleware to support. So what do we helping these projects? Again, this is the core program. How do we help these projects deliver on this? So we have set up a grid support centre based at the Rutherford Laboratory, Manchester and Edinburgh, which offers user support. So you can call up and somebody will help you. You say, what's happened to my job? I submitted a job and it's disappeared, and they will help you find out. Is it a problem with the network? Is it a problem with your local end or whatever? It also operates a grid certificate authority. That sounds an easy thing to do, to issue digital certificates for authentication. Actually, there are lots of policy issues to be sorted out, and we're going through what Bill Johnston described as a cycle. First of all, you do it once, then you realise you did it wrong, and you start again. So we're in that cycle. We're beginning to learn what's needed to do to really run a sensible grid certification authority. And they're working closely with the data grid colleagues in the UK to learn what the data grid project has been doing. We're also supporting, as you heard from the NSF middleware initiative, they've just issued their release. We issued a similar release with Globus 2, Condor and SRB, and we clearly need to talk to them about how we maintain that and migrate that through to Globus 3, for example, as you heard Ian talking about. And also pick up again a library of open source grid middleware that's being developed by other projects like DataGrid and so on. So that's what this support centre does. And again, in order to build a grid, you really need an engineering task force. You need to actually make it happen and to actually get people, the right people at each site, and it's not just the computer scientists, it's not just the computing services, you have to get all these people together. And so we have an engineering task force whose job is to build a persistent UK grid. And I think we're at stage one, everybody's running the same software, but it's actually, what we're now doing is developing test applications which can really stretch and make sure that we can use this in a way that we could offer to industry, for example. We also offer training courses at Globus now on web services and OGSA, and those you'll find on the web, and you can take advantage of them if you want. This is the website, National eScience Centre in Edinburgh, you can look at there. And they also run a research seminar program, multidisciplinary workshops, and again, you're invited if you have a workshop topic that you think is really key. The purpose of these workshops is to be international, multidisciplinary, and you can suggest things and assist, and we can provide some money to make that happen. So there was a thing on Blue Gene, the IBM Blue Gene project. There was a China meeting of N+N with N scientists from China, with M from the UK. There's also one planned on grid performance engineering. But you'll look on the website, you'll find a more complete list. We believe this can't be done by the UK alone, or Europe alone for that matter. We do need to participate internationally, work with the international community, and that we're doing through the Global Grid Forum, and we're funding people to go there. We have some fellowships for people to go and work in the US or work at CERN on grids. And we're hoping to have, we have informal links with San Diego Supercomputer Center and NCSA, the two NSF sites, both of which are involved in the TerraGrid, for example. We're hoping to formalize the exchange of information and the alliance there. And we have had a meeting with the NSF on grids last summer. Appropriate for this conference, John Crowcroft at one of our meetings, the first meeting of my technical advisory group, suggested setting up a grid network team, and this seemed like a good idea. And this is an expert group whose job is to identify the key issues for people when they run their eScience application. From Imperial College, they want to use a computer in San Diego or Edinburgh, access a database. These end-to-end quality of service issues. Will their eScience application packets get swamped by people doing web searching or email or whatever? And that's one of these issues when you have a complicated end-to-end chain like this. This is the backbone here, but don't forget you're sitting off one of these metropolitan area networks and you have to go through those. Maybe you need occasionally to bypass them, maybe you need to use lambda connections. These are all the sort of issues that we'd like to explore. So we have a project which John Crowcroft can tell you more about on traffic engineering using MPLS to give you a sort of differentiated service, diffserv, for differentiating the quality of service for different types of packets. That's involved Cisco and Ukerna. And we're also funding an extension to the DataGrid project with the PPARC funding as well, looking at bandwidth scheduling, and John Crowcroft will be talking about that this afternoon. So these are projects that we think are necessary, but not sufficient, but at least we're making a start. We also can, because we believe, to convince the community, we need to convince industry, and we need to convince the politicians that this is a serious agenda. We've funded a number of demonstrators, which you can find out about, which actually are really, I think, many of them quite impressive. So they have been done using part of standard software and part, a cobbled together software. So this is what the grid could do in the fullness of time, and you can get a vision as to what it could support. We also have analysed some research challenges, and these are the ones for computer scientists have looked at. Semantic grids, trusted ubiquitous systems. Ian's talked about a level of services, and when you want to put together many of these services together, how are you sure that they don't clash, that they actually do what you want them to do? Provability of those sort of customization of services is one of the issues that the computer science community believe they can contribute. Ian talked about autonomic computing. That's when I run up the stairs here, my heart automatically goes faster, giving me more air. I don't have to consciously think about it. So the question is, can you make this middleware as autonomic as possible, that it's self-tuning, self-organizing, self-optimizing, without having these systems are very complicated. If you can make the system intelligent enough to do much of that for you, then it is clearly a big win. And again, there are many other issues, sociological issues, new forms of community and the impact. So those are the challenges that were identified by our community. These are some thoughts as to possible future initiatives that we're looking at. One is the possibility of an all-Ireland grid. We have an eScience centre in Belfast. It would clearly seem to be an interesting exercise, a cross-border exercise, to do something with the Southern Ireland grid activity. And so one of the things we're talking with the Science Foundation Ireland about the possibility of a joint project. Another one, which is obvious as a possibility, is some sort of joint initiative where we can complement the activity going on in the NSF middleware initiative with both the grid and the Internet 2 activities, both of which I think are complementary and converging. So we would like to play our part, and the emphasis on data that we're doing is at least one part, and we're working closely with the Globus team on that. And again, we have R&D programs, and typically the research councils or the NSF type people fund research. What's difficult to fund is development. We have this Joint Information Systems Committee. They're the people who fund the network. They fund, if you like, development activities. So we're thinking of having a joint program with the Research Council where the Research Council fund the research and JISC fund the development on things like semantic grids, autonomic computing, and so on. And again, we've already had a joint project with JISC, with NSF, with Internet 2, where we've done a similar thing. Why don't we do it in the UK? And what's missing from this slide is another bullet point, which is European efforts in Framework 6. Now, that's letters of intent have to be in, I think, by the end of this week, so perhaps it's a little late to put an expression of intent at this moment, but that's not absolutely necessary. But there will be calls going out for grid activities in Framework 6 by the end of the year. Roman Turler's here, so you can ask him. And that's a real opportunity for Europe to contribute to making this whole activity really work. So these are some technical reports you can find, and you can find also more details of all the projects I've talked about on this website, so I invite you to have a look at it. Summary, the projects that we have to support in the UK, what the grid means for the UK is what's needed to support the projects we have. And those are emphasising data and data federation and access and searching as much as computation. So metadata and ontologies, we believe, automating the process of putting metadata on this stream of data coming, using ontologies as shared vocabularies between different communities so that they can work together and reason about their data. And we believe that we have some unique elements here because we have a really focused program on people and middleware, significant sum of money, and also linking to industry, covering the whole range of science. So there's some interesting things there. And why I think it's interesting is because this is what my boss said. eScience has the possibility of changing the way you actually do science in universities all around the world. It really could have a major impact. So it's a really bold vision, exciting challenge. I also think there's another element, and I think you've seen that the internet and the web and Linux have had the power, people power, to change big corporations like Microsoft and IBM. IBM put $1 billion into Linux last year. Why did they do that? Well, it wasn't an accident, right? It was clearly a commercial decision. And Microsoft abandoned their plans to go their own route on the internet and followed the web. Again, people power can have an effect. And I think the grid, if we do it right, can have a similar effect. And if you want to know who said that, so you can hold them to it later on when it's either right or wrong, it was me. So by all means, call me to account later on. And I think the kick-off started about 2 minutes ago. So thank you.
Well, thank you very much, Tony, for this interesting list of projects and the activities which are quite active in the UK and elsewhere. Despite the kickoff and people are leaving in troves already, I think there are those of you who wish to ask some questions. I think there's some time left to do that. And please feel free to ask some questions now. There are two microphones in front of you, and any questions to any of the two speakers?
So while we're waiting for people to think of a good question, I wanted to say one thing I forgot to do during my talk, which I meant to do, was to point out that outside there are some very nice demonstrations of two projects which are actually doing grid stuff for real, the EU Data Grid and the Unicore project, so as well as a number of talks. So I didn't get to that, probably my jet-lagged state, but I wanted to make clear to acknowledge that.
Right. First question.
John Crowcroft. Hi. So I'm going to cause some trouble.
Surprise.
Yeah, good. One thing, there's a lot of good stuff in the whole grid program, and it's really cool, but there are at least two bad things happening. One bad thing that's happening is people are reinventing square wheels for networking. For example, we heard earlier about the tsunami protocol, which is a way of getting 800 megabits as a way of doing things much better than TCP will ever do, despite the fact that TCP has been run at a gigabit already. And there are ways to make it go faster. And we've also heard about grid projects which are building wonderful layers of middleware in Perl. Has anyone ever tried maintaining more than 100 lines of Perl? I mean, forget it, right? You think, buying into 10 million lines of Fortran, the way physicists have done in the past, would have taught them a lesson about software engineering and maintenance. So I'd be interested in the panel's opinion about how we manage to avoid these short-term mistakes and keep the long-term vision informing every project. I'm only giving two examples. There are many, many good examples of grid projects, and those are two little things being done by the European Data Grid and some projects which are very scary. So I'd be interested in how people keep us on the straight and narrow, as it were.
Well, do you want to
So, John, you're right. We should be using shell scripts, not Perl, right? I'm not sure I have any great words of wisdom except to say that certainly this is an opportunity and to embrace more modern software engineering techniques, and I'm very encouraged to see the number of people developing pretty sophisticated services in things like Python and Java, which is at least a step forward. Yeah, I'm not sure how we make the right connections between the networking research community and and people working on high-performance network protocols. It's certainly true that, the people who developed Tsunami, did it because they perceive a real problem, and what perhaps the solution they've proposed is not the right one, maybe, but the individual scientist does have problems with moving data from A to B, and perhaps the network community could get more involved in trying to provide end-to-end performance diagnostics, for example, that would work transparently and automatically and address some of these issues, and then we wouldn't have this same need to solve problems at different levels.
Does this? Oh, all right. Just two comments. One is I really welcome the move of Globus towards a more modern component-based software technology, and clearly there are problems with Perl and scripts and so on. I don't have any instant answers to those. On the networking, it seems to me that this meeting is a good example of what's needed. that you actually have to bring these communities together so there is mutual education. I'll give you another example. You see, at the moment we have access grid nodes in our centres. Now, I'm not sure that access grid nodes are the right way to go. Certainly they do some things that people like for collaboration, but they're not H323 compliant. And there's VRVS, and that might be a way to go. But then I heard Internet 2 say they wanted to do yet a different one. Now, I don't know which is the right way, and I think the only way is to get the people, the experts in the room, with people who have clear needs. So I think bringing together multidisciplinary communities is a start, and that's why I think I welcome the focus on grids at this meeting. I think that's an interesting start, and I think that's what we have to do. So that's one of the reasons why we set up the eScience Centre in Edinburgh, eScience Institute, which was to get communities together. So, John, maybe you and I should get our heads together and to see who we should get together so we get them talking and so that they at least know what's going on in a different community. If they then wish to ignore it, you can't do anything about it. But I think going forward with broad consensus, with informed consensus, is the only way in a community as anarchic and wide as ours.
Thank you. Any other question? Yes, one. Can you state your affiliation, please?
Bob Morgan from Internet 2 and University of Washington. Maybe another bristly question. I think obviously lots of folks are interested in OGSA and how it's happening. Maybe the question is to clarify the nature of the work that's going on within the sort of Globus and IBM team versus the work that's going on with the OGSI group within GGF. It's my understanding that the majority of the architecture work is going on in the within the traditional team, and it may have limited visibility from the outside world. Maybe that's my mistake, but for those of us who might want to get in there and exercise our own wrenches on that stuff, is the GGF the right forum to do that in?
Yeah, no, that's obviously a good question. So, I mean, we're certainly trying very hard to make this proceed in an open fashion, and I think we're doing an okay job. I'm sure we could be doing better. But yes, there's an awful lot of traffic on the OGSI working group mailing list. There are some people, for example, Peter Vanderbilt from NASA, who are making a lot of good contributions. I think the core group has been a bit slow in terms of getting revisions to documents out for people to look at. That's not really because they're doing work internally, it's just that they haven't been making progress. But they have promised to get those documents out in the next few, actually I think they have promised something this week or early next week. There was an initial set of revisions based on feedback provided a few weeks ago. We also held a small workshop at Argonne for early adopters of the reference implementation, which had about 80 people at it just last week, and that I think gave a lot of helpful feedback. And we encourage people to keep reading the spec, provide feedback, try the implementation. Yeah, and if anyone has any advice on how to make the process work even more effectively, that would be really, really appreciated.
Yes, I mean, we have a vested interest in the UK in making sure that the Global Grid Forum is an open forum, and so we've set up with the GGF a working group on database interfaces and OGSA, and we will do our best to make sure that really is open and that we link in with the main OGSI. I think what will cause a change is that the moment you have IBM and a few, if you like, minnows, but who are really interested actively in participating, but I think you'll see increasingly people like HP and Microsoft engaging more closely, and I think that will take the process forward and I hope make it into a genuine open process. So I'm an optimist, but that's how I see it could go. Doesn't necessarily mean it will, but it could.
Yeah, I was going to add, I mean, I see this, I mean, I'm really concerned to see additional significant industrial involvement, because I think that's critical to keeping IBM viewing this as an open process. And so we've been talking to Sun, HP, Microsoft, and also some other smaller companies about getting them involved.
Yeah, that's great, and that's really important. I think we're all aware that web services is a major, both open and potentially, newly proprietary effort in the industry. There's obviously a lot of great forces at work there, and a lot of potential for all those parties that always have a proprietary interest to make things proprietary. So, to the extent that our community overall can help those folks remain open, we're obviously all better off. So.
Well, thank you. I think there was one other question. Somebody was rushing to the...
Thomas Scheffler from T-Systems, Germany. I understand there's a need to broaden the application base for grids, but I think currently, everything which comes with a grid label gets to be accepted in the community. I somehow fail to understand, for example, how a multiplayer game is going to be the grid of tomorrow. I think, to me, I think it needs a bit more tightening of what we really are going to achieve. And multiplayer games are around since a long time, and so does this mean we have the grid since whatever?
Thank you.
Yeah. So my favorite so-called grid proposal was one for actually it was taking some embedded systems with FPGAs and saying that you could use it as a grid application, grid's middleware testbed, which I thought that was really stretching things a bit. Yeah, the multiplayer game example is not. I think it is a good example of grid computing, but it's not because multiplayer games. It's not so much because of the multiplayer games in and of themselves, but because of the desire to do dynamic provisioning of the back-end resources that will support them. So they are putting together a collection of computing and storage resources at multiple IBM data centers. They're doing this in collaboration of IBM in fact, around the world. And then they want to do dynamic load provisioning between those resources. So that's the part of it that they are calling grid computing, and for which they propose to use some of these technologies. And I think that's valid, and I think will be typical of a broadening range of applications in industry.
Well, thank you. Yes, I think that is probably the last question.
Okay, this is David Williams, CERN/Terena. This is a comment, but it may provoke a reaction from the panel. Is actually to tell people in the audience that the technical advisory group, which is sort of the body of the Terena membership that met on Monday, identified this whole issue of AAA support as one of the key issues that faces the Terena membership and the whole Terena community at the moment. The point is that we have international communities, many triggered by grids, that require this support. It has to be integrated in some way, and we're not claiming to know the answer to which way yet, with national approaches and with the individual universities. So we actually have to work out in Europe what role the NRENs want to play in this in each country, and how we want to integrate the national approaches into some reasonably coherent European approach.
Well, do you want to say, Tony?
Yes, I mean, the standard funding through JISC rather than the research councils in the UK is, if you like, the NREN funding. And I was heartened by we put out a call for at least an initial surveys as to what to do. We hope to put out a later call where we actually do substantive, when we've decided what's sensible to do. But certainly talking to the Internet 2 people, talking to the Terena people is clearly on our agenda, and Alan Robiet's here, and I hope listening. And we would like to play our part. But at the moment, we're just really finding out where in the space we could do something sensible. So I don't have the answer at the moment.
Yeah, I'll just add one of the things that we hope will come out of the NSF middleware infrastructure initiative in the US is a better understanding of how to integrate grid and campus infrastructure. So one of the experiments we're currently engaged in with the University of Florida and the Sura group is looking at how we can integrate the Florida campus Kerberos infrastructure with the larger grid public key mechanism, so that Florida people can sign on using their regular Kerberos schemes and then transition into the public key credentials they use in general for their physics or whatever it is computations they're doing.
And just to make the point explicitly, I mean, life is even more complicated in Europe because of the different ways it's done in different countries.
Well, thank you very much, and thank you for the patience that you avoided the risk, and thank you to both speakers. Thank you very much.
Thank you very much.
Thank you. Thank you.